Hello everyone, welcome to the 9th lecture on reinforcement learning. Today we're going to be learning about model-based reinforcement learning methods and how we can start to integrate learning and planning. So model-based methods are really kind of like the third form of function approximation. So we've used function approximators in the past to approximate the value function, and we've used function approximators to approximate now the policy, and now we're going to start to talk about how we can use them to approximate the environment. So in this overview today, we'll be going through kind of just the definition of model-based reinforcement learning. Again, talking about within the context of function approximation, how we've kind of come full circle now to approximating nearly every part of the reinforcement learning problem, the value function, the policy, and the environment. But as with most RL techniques, today's content can really be used like as another plug-in to most of the RL algorithms. But the challenge is, again, learning what the characteristics of it are, how and when to apply this new form of function approximation again. So we'll start with just a taxonomy of the literature, of how the approaches sort of can be thought of and how they fit together within the context of the literature. And then we'll have an overview of the differences between model-free and model-based reinforcement learning. And we'll look at the cycle of model-free learning and how this cycle can kind of be extended with simulation. So before we've mostly just been training from experience, but now we've had this cycle where we experience some of the data and we update the value function or we update the policy and then we experience some more data. But now we're going to sort of add another inner loop to that cycle where we can start to train not only just on experience but also on simulation. And this leads us into much more data efficient agents which can imagine actions both in the past and also imagine rolling out future actions without actually taking those actions in the real world. And then we're going to look quite closely at the advantages and the disadvantages of doing this. So with all that context, I'll then formally introduce the definition of what the model is and how this can be learned via a function approximator, such as a deep neural network, just with simple supervised learning at the end of the day. It's basically like you're training a classifier or a regressive model. You have to classify the actions and regress on the reward. Classify the states that you're going to transition to and regress on the reward. And then basically we'll discuss the differences and definition between real experience and having simulated experience. And this actually will lead us into a nice integrated algorithm called Dyna Q, which is in Sutton and Bartow's book. But this basically uses both real experiences and simulated experiences to really get the best of the model-free literature and the model-based literature. So we use the model-based methods to do our planning, and we still use the model-free methods to get a nice estimate of the value function. So we'll outline the characteristics of Dyna Q and we'll see how it improves exploration in a simple maze environment. And lastly, we will look in a bit more detail at two more recent algorithms or two more recent techniques, one of which is used to solve the game of Go, which was very famous. And it does this by planning into the future. So sort of given some state, it starts to map out a tree of all the states it can go to, and it visits those using Monte Carlo tree search, but all simulated, imagining the games into the future. So you don't need to just try lots of things against your opponent. You can sort of try and think, well, if I play this and my opponent plays that and I play this, where am I going to end up? What state will I be in? How much reward will I get in the future? So it basically imagines future games. And lastly, we will finish by looking at a recent paper that uses this kind of idea in Atari to simulate the future of Atari games. This is using quite a sophisticated neural network architecture, so we're mainly going to use this as an example just to sort of give some ideas of what kind of more advanced architectures can be actually implemented in these kinds of agents. Most of the architectures we've been looking at so far, yes, they've been deep neural nets and function approximators, but mostly they're quite naive things like just linear layers stacked together and so on. But we'll start to see, actually some of the design ideas we've been looking at in the deep learning submodule can be brought into the reinforcement learning literature as well, giving something a little bit more powerful. So let's just recap this taxonomy that we introduced in the very first lecture. We can kind of see how we've really extensively gone down the model-free route so far. So this is where we haven't really been explicitly building a model of the environment dynamics, And we haven't really even tried to understand such a model. So previously we've built up the foundations of dynamic programming, of Monte Carlo methods, and this actually led into Q learning. And all of these were just learning from our experiences of the environment, and we weren't actually modeling the environment. We then started to use function approximators to estimate the value function and to estimate the policy with the policy gradients lecture. But now we're going to be focusing on this sort of branch of the tree. And these methods, this class of methods, they focus on the model. So we'll be building a model of the environment dynamics. And we'll use this model that we build of the environment to actually plan and imagine and perform more effectively and efficiently within the environment. And it's actually, we'll see that in some cases it's actually easier to learn the model than it is to do the model-free based approach, and we can get some nice advantages from it. But there's not really such an elegant way to classify the model-based methods in the literature. They tend to be a little bit haphazard. But today, hopefully you will see that the techniques that are there, the kind of foundations, can be combined with the value-based learning approaches that we've discussed in the previous lectures, and you can really get the best of both worlds. But generally the model-based literature can be split into approaches that learn the model versus those in which we've got an explicit model is already given to you. And this actually has a lot of crossover with exploration and exploitation, as well as off-policy learning. Specifically, with a model, we can simulate our experiences without actually having to carry out actual actions in the real world. So, just an example, we can effectively imagine what our model will do. We can imagine what would happen. So, for example, if you tried to climb Mount Everest without, we're wearing nothing but flip-flops and a t-shirt and shorts, your toes would quickly get frostbite and you'd freeze to death. So you were kind of imagining if we were in this situation, where we were dressed in this way, we know we would die at the end because we're imagining that based on our experience. We don't actually need to go on into Mount Everest in that situation and experience it in the real world to know that's what's going to happen. Perhaps a better example, if you have a model of the rules in a game of chess, so it's quite easy to learn the rules of a game of chess, but then you can use that model to imagine what would happen if you moved your bishop to c4. And if you moved your bishop to c4, that would allow the opponent, maybe in his current state, to get checkmate. So you can sort of simulate that. You can simulate that movement and then see what your opponent does and then see what happens. And it seems that 9 times out of 10, the opponent gets checkmate. And the model itself can be quite simple, just only having to do some very basic rules, only follow the basic rules of the game. So the basic idea of today is that you can actually learn by imagining these situations of environment dynamics, and in many cases it can be much easier to learn the rules of the game, which can allow us to use lots of simulation of our model, and hence we can be very sample efficient. Alright, so just to make this clear, we can taxonomize reinforcement learning into 2 classes, into model-free and model-based. And with model-free reinforcement learning, there's no attempt to model the environment. So the agent makes no effort to model the environment transition dynamics or the reward function. Instead, it just learns the value function, or V of S, or the action value function, that Q of S and A, and or the policy function, the pi of the action, the distribution of the action, conditional on the state. And when we learn those things just by sampling from direct experience of the environment. So whereas in model-based reinforcement learning, we learn a model based on experience. So we construct an estimate of the transition dynamics and the rewards, but then we use the model to do planning. And this is where we estimate the value function and or the policy from the model. So planning means we use the model to look ahead and figure out what the right trajectories are, what actions to take. So if we have a model of the chess environment, we can use this model to consider our next move and the implications of it in the future by looking ahead with it and querying the rules and the transition dynamics that the model has learned. Okay, chess maybe isn't the best example here because it's deterministic, but in some cases, what happens, what the environment does is a little bit unpredictable. Like if you're in a snowstorm or some things might happen in a way that you can't sort of deterministically know what's going to happen, but we can still build a model of those transition dynamics. All right, so in model-based RL, we simulate the environment, and how this works is typically in the following simulation cycle. So the agent takes, you can think of the agent here, it takes an action in the real world, but then we have this simulation of the real world according to this action, and this predicts what the environment does and when you take an action in it. So in this figure here, the simulation is represented in the middle with this kind of matrix-like code under the environment, and basically this is meant to represent the actual real environment as closely as possible. So imagine like we're in this matrix. If you've seen the movie The Matrix, this might make a little bit more sense. But then we're in this fake world. You live in this fake world, and we imagine that the action of opening the fridge. We would try to simulate what's inside the fridge. We would try to simulate the contents and predict the next state. And the next state of taking the action of opening the fridge would show that the fridge contains milk, it contains eggs and cheese, and maybe last night's leftovers. But then if we are in the real world and we actually open the fridge, sometimes we discover it's empty because your partner made an omelette and a smoothie. So you correct your environment model then, and you update your predictive model based on this actual experience. So you keep them as closely aligned, but you can still use the simulation to imagine what's going to happen when you open the fridge. And we can actually train our simulation of our model this way, for example, using function approximators, deep neural networks, until we actually have a very good representation of the environment that captures all of its transitions and dynamics. And now, once you have this model trained sufficiently on your experience, you can use it to do planning. And this then follows, like in the previous lectures, where we learn the value function and all the policy, but instead of like the real world method, we basically just query our model instead. And actually querying our model can be very, very efficient because the model can be implemented on the GPU using a neural network. Whereas actually sometimes simulating the environment can be very inefficient. So we can actually also iterate, doing lots and lots of simulation and planning with our model, but we can only take real actions in the real environment very, very infrequently. So it's like in this loop here in the figure, we can do loads and loads and loads and loads and loads of iterations here, doing lots of planning and imagining tons and tons of things, and then only take like one step in the real world. If we have all of that computation available to us, or if this is really, really efficient and parallelizable, and this is very sequential and slow, and so on. Or maybe like this is a robot here which moves very, very slowly compared to the speed of the processor here and the hardware on the robot here. Okay, so is this useful? Is this a good thing to do? And some problems have a very difficult value function, or they have very difficult policies to learn. However, the model itself can be very straightforward. So consider, like, again, this metaphor or the example of the game of chess. Chess has about 10 to the 45 states, and a single bad move played at the very beginning can have this catastrophic change in your value function. However, the actual rules of chess are extraordinarily simple. So I taught my daughter them when she was about 5, and I taught her most of the rules in about an hour, and we were able to play chess games with each other, which she really enjoyed. But it's extremely simple to just say, you can move your bishops in this way, your knights in this way, the queen in this way, and so on. It's just a bunch of small rules. And the model can actually learn those rules extremely easily and extremely quickly. So if we can learn the model, which we say is often straightforward, we can then estimate the value function by just looking ahead several steps. So if we're playing chess with a model, we could do a kind of tree search, where we start in a tree of the current state and we kind of expand it out. So it's like all of the possible actions we can take, and then all of the possible subsequent actions, and we can kind of search through this tree to allow us to estimate the value function. And this would be otherwise very difficult to do via experience alone, and to learn via experience alone, because you would actually have to take those moves and then you would end up losing the game. So the model can sometimes be a simpler and more useful representation of the environment than you can otherwise access just by simple experience. And what's really nice is that you can actually learn the model just by supervised learning. So it's just like training a classifier or training a model to estimate some value given an image or given some state or observation of the environment. So for example, when you choose an action from some state, you can give these values to a function approximator to like spit it into some linear function approximator or a deep neural network. And then you basically see what this function predicts the next state to be. But when you actually take this action in the real world, you get the ground truth state of where you transition to, of where you end up. So you've got this really nice ground truth to use, and then you can just compute the error between where the model thinks you end up and where the actual environment says you end up. And that error term you can use as the loss, and you compute the gradient of the loss with respect to all the model parameters and update them up and down accordingly to minimize it. So it's not like we really need a very clever algorithm that goes to the end of the trajectories to learn all of this. It's actually quite simple to train. Another nice thing is that the model learns a distribution over what's going to happen, and this means we can actually start to reason about the uncertainty in the environment. So, for example, you can query the model to find out what's probably going to happen to some extent, and you can actually use this distribution you've learned to quantify this probability and this uncertainty. And that's often a lot more, well, it's very useful in cases where, if you want to maximize the likelihood, or if you want to have some, if you want to end up in some state, but it's very improbable to get there, you can have this kind of justification available to your agents, this reasoning ability available. So there are some disadvantages of model-based reinforcement learning. Of course there are. And so the main disadvantages are that we're yet now adding another component into our toolkit that we've got available, but this new component introduces yet another type of approximation error. So it's just another function approximator, and of course it's not going to be perfect. It's not going to be a perfect model of the environment, and these things really do start stacking up, all of these imperfections. They have implications on the convergence and the stability of your algorithms. So before we could get errors in our value function approximator or in our policy function approximation, now we can also get another type of, we're now introducing another type of estimator. So these biases and errors can further be introduced here, and they do add up. And later we'll also see that we can only really be as good as our model. So if we learn an incorrect model of the environment, then this will actually be our limiting factor, and we'll get incorrect results when we do the actual planning. To tackle this, we'll later try and combine the advantages of this model-based and the model-free methods into a single unified architecture, which hopefully gets kind of the best of the worlds. Okay, so what is a model? Let's try and be a little bit more formal here. And there are several ways we can define it, but one way is to simply say it's a representation of an MDP. So if we assume there's some underlying MDP which dictates the rules of, say, the entire universe or the specific environment we're interested in, and we say this MDP, this governing MDP, the MDP of the natural universe, it's in some state space. It's in the states are in some space, so they could be in pixel space, the space of pixels. If you're in some kind of 2D environment, or it could be in some 3D space. It could be in some sort of space of just chessboard pieces or so on. And then there's also some action space, so like the space of possible actions you can take in your states, from your states, whether it's like to move actuators on a robot, or whether it's to control a helicopter or control a car. You can take some actions. And there's also the transition probabilities, that P, which tell us what is the probability of transitioning from one state into another state. So it's very unlikely that you'll transition from the state of sitting in a chair to suddenly being in a swimming pool. You have to next transition to the state of getting out of your chair and then walking to the swimming pool before you can get into that state. And finally, there's the reward function R, which is basically most of the time it's zeros, but you get reward if you win your game, or you get reward where if you move your robot quickly according to whatever your objective is. So specifically, the model tries to capture the distribution over the next states conditional on the current state action pair, the action value or Q. So when we sample from our transition probabilities, we try to learn this distribution of the next state, conditional being in our current state and our action. So it's like, it can be, it's non-deterministic, this distribution. While we could have a deterministic model if it was a deterministic environment, we still would try to estimate the probability that we would actually end up in one of these future states. The probability that I would end up in the next point in time standing up from my chair would be quite high, maybe even higher probability that I would just keep sitting down in my chair, and it would be a very, very low, near zero, well, it would be a zero probability that I'd end up just suddenly teleporting into a swimming pool. Okay, so it's conditional on the current state action pair. So again, if I was in this chair state and I was considering the action of standing up, then my next state would be, I'd be here. I wouldn't be in a swimming pool. But from this distribution, it tries to estimate what the reward will be when we sample an action from it. So is there any reward from me standing up? Well, not really. Is there any reward from me being in a nice place in the Andes Mountains in Arizona with a beautiful view? And then, yeah, you could say there's a nice reward there. Would there be any reward for dying in a car crash? Then you could have a very negative reward because you don't want to die. And again, the reward's probably easier to think in terms of like a game of chess, where the reward is just you get zeros everywhere, so it's quite easy to learn. But when you're in the conditions of checkmate, then you get some reward. Okay, and basically it's just a function approximator which tries to predict what if you're in OpenAI Gym, you get that environment.step function. It's basically just trying to predict the outputs of that. So some literature likes to think of this as like a joint distribution over the next state and its reward, conditional on the current Q values. But typically we say that these two things, the next state and the reward, we say that they're conditionally independent. So this last equation here is just saying that. So we can just estimate the distribution of the next states, and we can just independently estimate the probability of our next reward, and we can just multiply these together. But some like to consider there's a joint distribution between these two that we wish to learn. But typically you can have like two different functions for estimating it. So one question you may have is like, what's the difference between the model estimating the reward and the actual value function itself? And it's important to distinguish here that the difference between learning the reward function and learning this value function, and David Silver likes to explain this with the chess analogy. So if we're playing chess, it's very easy to learn the environment reward function because it basically is just zeros everywhere. You don't get any reward if you move your bishop to c4. You only get reward when you're in checkmate. So it's very, very easy to learn that function with the rewards. But it's much more difficult to learn the value function. So if you remember, the value function involves looking ahead and calculating the return. This is actually quite difficult to calculate in a game of chess. So let's say you're halfway through the game of chess. You need to learn the value at all of the intermediate states. So you need to learn like the probability of winning if you've taken all of those various actions available to us, and the actual value you get from those actions you've got available to you. And that involves lots of rolling forward and thinking of all of the future moves, and you've got 10 to the 45 states. So it's a much more difficult game, a much more difficult quantity to estimate. It's a much more difficult problem than just estimating the reward function. So in summary, there are situations where learning a model of the environment can be much easier than actual planning, and we can use this model for several advantages. Okay, so how do we actually train the model? Well, it's quite simple. We receive this stream of experience from the agent in the environment. So we're in some state and we choose some action. And then we observe the reward that we get, and we observe the next state that we transition to. And this little bit of experience becomes an example in our training data set. So you can imagine just pushing that tuple of information into some dataset buffer, like an experience replay buffer. And then the model just samples from that dataset, and we simply then just do supervised learning. So the input of our model to our function approximator, it's just the states and actions, and it tries to predict what the reward will be. And just predicting the reward is a very simple regression problem, so you can use like mean squared error. And you also try to predict what the next action will be as a distribution. So it's like a categorical distribution where you can just use cross-entropy loss and do a softmax over the outputs to ensure that they all integrate nicely to one. But it's basically just a classifier at that point, or it's classifying the next states that you're going to transition to. That you can use your cross-entropy. So in terms of how your model should be parameterized, this again can just be any function approximator. It could even be a table lookup. It could be a linear expectation or Gaussian model. Typically we're going to be thinking about neural networks, deep neural networks as our function approximators. But I'm not really going to dwell on the tabular methods, those big table, how you can just, like in the traditional methods, use a big table for your model. As they're not particularly that useful in the very large RL problems or the exciting ones. But basically, your model can literally just be a big NumPy array where you would store a global count for every state action pair. And then from a given state, you would basically count where you end up in. And you would use the empirical counts renormalized by the total count. So you can basically get a probability distribution that tells you where you're going to end up in from a given state. You just do all that in a big table. But it's much nicer if we can start to think about using function approximators which can fit to the interrelationships between the states and get a nice estimate. And these actually can generalize a lot better. Alright, so now we're going to try and merge together the advantages of model-based methods and model-free learning. So we're going to discuss the methodologies that utilize both to try and design some kind of superior or some kind of very flexible agent. And basically this agent is able to learn from real experience, but also in some kind of inner loop it's going to have simulated experiences. And then so we've got these two sources of experiences that it can learn from. And we can sample these simulated experiences from our learnt model of the environment. And this is just some function which we say is parameterized by eta. So here is eta here. It's just like we've had the theta, and we've had the weights as w, and now we've got eta as another form of our model parameters. But we also less frequently we sample from real experiences from the actual environment, or from our true underlying governing NDP, the natural data in a natural universe, or our robot sampling its pixels from its actual hardware sensors rather than imagining. So you can imagine this robot in some environment, it learns the environment that it's in, maybe it represents it some way, and then it has this inner loop where it tries to plan where it's going to go to avoid the obstacles or to avoid the things that might cause it harm. Comes up with this very good plan after lots and lots of iterations and refinements to maybe move around the obstacle with this series of actions, and it executes that plan in the real world. And then it actually uses the real world experience of actually executing that plan to refine its model again. And we're going to see this now more practically in what's called the Dyna Q algorithm. So this is the Dyna Q algorithm outlined here, and it's really just a kind of straightforward implementation of what we've said so far. So we start off with some action value function, or this Q, and in this example it's just a tabular method, but again this is just an example. You can use the function approximator ideas that we've seen so far. And then we also have this model here. This is another function approximator, and we're going to use this for our planning. And again, this can be a big table, or you can swap it out with a function approximator. It's very sort of plug and play. All right, so the Dyna Q algorithm, what does it do? Well, it iteratively updates until it reaches some terminal state. So until, if you remember our frozen lake grid world, it will just iteratively update, moving around the agent until you fall into the water or find a frisbee. And we start with just some state, which is just our current state. It could be wherever it is. And then we from that state, we choose an action with, again, an epsilon greedy approach. So it's sort of got a bit of exploration in there, but otherwise it exploits the current Q table. So you pass Q into it, which is like choosing the best action from Q with a bit of stochasticity, a bit of randomness. And then we basically put this, we execute this action in the real world. So this is where we call our gym environment.step, and this gives us our reward at that, and the state that we've transitioned to. So the reward from taking that action and transitioning into the state, and the actual new state. And this is what we want to learn. Okay, this is what we want our model to learn. But we basically do our Q learning update now. So this is all the same as you've seen before. So we update the value function here a little bit by this alpha in the direction that gives us the maximum value after this kind of one step look ahead. So we learn the optimal policy here. Okay, so this is all very standard if you've gone through the TD learning lecture. But then here's where things start to change a bit now. We now update the model here, and this is just using supervised learning. So it's very easy to do. So the model now gets a prediction of the reward, and it gets a prediction of the next state. So it starts to learn to estimate in this way. All right, and now we have this another inner loop, and here's where we're going to start doing our planning. So basically, in addition to the real Q learning, it's like the agent closes its eyes, and it has this inner loop where we're going to just start imagining and simulating from our model more scenarios and imagining more situations, and we're going to draw from that knowledge. So we learn from our imagination. This part here could be like saying, what would happen if I instead chose this action in the past, or if when I was back in this state here, what would happen if I moved my bishop to b5 rather than to c4? And now let's kind of play this game and see where it ends up. And so this is based on the rules that the model has learned, and also based on the transitions that the model has learned up to this point. So again, let's just run through this more formally. We start we pick some random state from something we've been in the past, or something we've already seen, and we sample some action that we've previously known we can take these actions in this situation. And then we see what reward we get, and also what state we would end up transitioning to according to the model here, according to the simulated model and the environment we're imagining. And then we apply the Q learning step according to that imagined transition, so according to this updated value here. And then we take the max Q over this over our action value function. Okay. And we iterate this loop, updating our action value function, according to this simulated experience. So it allows us to imagine out those situations. And that's really it. It's just the same as standard Q learning, but with this additional step in here where we learn the model and imagine from it. All right, so how well does this actually work? And here's an example straight from Sutton and Bartow of the Dyna Q algorithm in a very simple maze. And basically this is the maze up here, and it's the same as our previous grid world examples. And you start in some state here, and your goal is to avoid these walls over here and reach the goal state over here. And in Sutton and Bartow, he describes these as just being solid walls that you can't pass through. I would like to just modify and tweak this a little bit, just for another example. Just imagine these are like the hot water in our frozen lake environment. So if you fall in these, that's bad, and you get negative reward, and you terminate. So imagine that you lose a reward for every time step you make. You lose a lot of reward if you fall into this water. And the objective now is to just basically try and find this goal up here as quickly as possible. And basically what this graph is showing us is that with no planning, or with the blue line here, And if we go back to our algorithm here, this is the case where we set n to 0 here, so that we never enter this planning loop. So with no planning at all, just like direct reinforcement learning, like it's basically traditional Q learning, it requires about 30 episodes before we can find the goal reliably. So you need a sort of maybe 27 or so episodes before you're in a stable position and your agent's able to finally, after enough exploration and exploitation, it finds the goal eventually and exploits that. However, if we start to do planning, so we allow ourselves to, we learn that it's bad to go in here early on, and then we imagine that if we take the action which means that we fall into the water, that's a bad thing. So if we allow ourselves to plan in this way, then much more quickly we can figure out the goal. So now if we do planning, you can see the amount of planning, so the amount of n you put in here, you can see that with just 5 steps or 5 episodes, sorry I should say, you can quickly avoid this hot water or this wall, and you can see which states are reachable from your current state, and you can advance much more quickly because it knows that it can get to sort of this state by transitioning around here. And it doesn't, it knows how to reach the extra states more quickly, and it can do that all with less experience. And with 50 planning steps, you can see almost immediately it figures out where to go. So it becomes very data efficient or sample efficient. So this is like Sherlock Holmes, thinking ahead of all the possible scenarios and assessing where they will end up before choosing a very sensible set of actions to execute in the real world. So another reason this might be good is that executing actions in your environment might be very computationally expensive. For example, if you're training an agent in a game or in some virtual environment, the agent might have to evaluate lots and lots of code on the CPU to simulate what happens next in the game. And the model, however, might be very efficient. It might be a deep neural network implemented with a heavily optimized back-ending CUDA, and you can do far more evaluative steps in every query in the real world. So with a model, you can typically maximize the occupancy of your parallel hardware, and this can lead to significant improved data efficiency. Alright, so looking back at Dyna Q, you'll see that we're just sort of randomly picking previously observed states and actions according to our simulation. So here we're just sort of randomly picking from our previously observed states and actions. But can we actually do better than this? Can we, instead of just sort of looking at the past states we are in, can we actually plan into the future? Can we imagine into the future? So imagine we're playing chess. Can we put ourselves in our opponent's shoes and then put ourselves back into our shoes and roll forward playing an entire simulated game? And the answer is yes, using an algorithm which is called Monte Carlo tree search. And this algorithm is what's used to play games like AlphaGo and AlphaZero. And the basic idea is that we just roll forward from our current state. So we're in this current state with our bishop, and we consider this is like the root node of our tree. And instead of computing the entire MDP, so instead of just randomly going to states from before, we just sort of zoom in on the current little bit of the MDP that we're interested in, and we roll forward from here. So from an initial state, this root node in the tree at the top here, we basically sample many trajectories of plays, and we do this successively. So I should say, as we do this successively, we learn a distribution over the actions available to us, and we try to figure out how much value they end up leading to. So we can then sample from this distribution as we learn it. So it's effectively like importance sampling. You try to learn, whether it's how good it is to take this action or this one here, based on the action value functions. Sorry, how good it is to take this action and end up in this state, how good it is to take this action and end up in this state. Okay, so this basically gives us a distribution over the actions here, and then we can sample more from the actions which give us the most total future reward going into the future. Sorry. So after sampling and doing lots of simulation, the return generated by the simulated episode from rolling out with our model is basically backed up now all the way to the initial action. So it's backed up all the way to the original action values, and this is where the initial rollout of the tree began. We don't actually save the values computed during the tree rollout phase where we look forward, but basically this allows us to compute very, very relevant returns for the current state that we're in, and we use all of this simulation, all of this imagination to imagine where the games end up. So we then know, like, from the current state with this simulation, by rolling forward, which options are the best. So it's not like there's just the whole MDP, it's localized and prioritized. All right, and now just to sort of conclude the lecture, I'll finish on a very recent paper in this area, and this was actually an ICLR oral spotlight presentation from last year. And while it's not particularly novel in any way, it hasn't really introduced any more ideas than what we said today, it does make some very sensible design choices for the actual architecture, so it is worth studying this. And also it's for Atari, which is a particularly nice bonus. But basically the architecture involves taking 4 consecutive frames from the Atari game, and this is using the pixel version of the game, not the actual RAM version. And I've actually had a couple of questions about, like, which is better and in which situation, and really that's like, it depends on the depends on a number of factors. It depends on, like, what's in the RAM itself, whether the RAM's encrypted, that would be almost impossible to use, or whether the RAM contains lots of useful states. And sometimes the RAM can be huge, like if you've got a 12 gigabyte game, a modern game, and the pixels can be comparatively small. If you've just got a sort of 720p image of pixels, then it can actually be more efficient to train on just the pixels. So there are lots of implications and reasons why it's sometimes better to use RAM and pixels, but in the Atari the RAM is very, very small, so it's quite easy to train with. But anyway, this particular architecture trains on the pixel version of the Atari games, and it takes as input 4 consecutive frames, so that helps give the model some kind of trajectory of where things are heading. And it also takes some input action as input, and it encodes these actions into like a one-hot encoding vector. And it basically has this U-Net-styled architecture with these skip connections here, and it tries to predict the next frame conditional on these 4 input frames and the input action, and it injects these actions into the kind of bottleneck parts here. These are one-hot encoded, and it's injected into these decoder layers, and specifically, these action layers get reshaped and then multiplied by the output channels of the decoder, and this all estimates to estimate the actions at inference time here. It actually uses here a recurrent architecture. This is an LSTM. This estimates the action autoregressively instead of actually sampling from a prior distribution. But this is all quite a complex architecture, but you can see it kind of makes sense why you would want these skip connections here, because you want to predict the next frame, and this is going to be very, very similar, or the geometry here is going to be very, very similar to these 4 input frames here. You can imagine edges here are in similar locations, and so if you didn't have these skip connections here, you would get quite a blurry prediction here. This will give you a very nice crisp prediction of the next frame, the next state. Okay, so there's several tricks in this paper, and I hope this gives you an idea of the kinds of things you can do to try and build a more sophisticated architecture, in particular for your coursework. And this one here is perhaps a little bit overly complex, but it is interesting to see the kinds of design choices you can make, and the design choices researchers are implementing. And maybe this will give some sort of ideas and insight into the kind of functions you can experiment with for the various components within your Gravatar assignment. All right, so that concludes this lecture. So in summary, what we've seen today, we've seen that model-based methods are easy to train with supervised learning, and they allow us to plan ahead. They allow us to go into that inner loop and we can either just sample sort of randomly, or we can actually roll forward with like an expanded tree out from where we're currently at and really think of the implications of the actions we take. And this can actually lead to a great deal of data efficiency. So we can have some kind of simulation where just with a few steps of actual experience we can get these amazing novel trajectories through the environment, which are clearly very intelligent, but it's actually done a lot of processing under the hood to imagine those situations. And this can therefore be used to imagine all of these situations without actually having to experience them, which is a good thing to do. It's what we do as humans. But we've seen that the value in the policy learned can only really be as good as the model itself. So the model needs to be good to have good planning and effective planning. However, it can be combined nicely with the model-free methods like you've seen in Dyna Q, where you just have that bit at the bottom where you just do more updating to your Q values. But there is like this additional bias and errors introduced in doing this. All right, so that's this lecture. It's another useful tool to have in your toolkit, especially in cases where you need to be more data efficient or sample efficient. So I hope you find this useful, and have a good week.